Astronomy to GCSE, Topic 1.3, the Sun. So 1. How can amateur astronomers observe the Sun safely? Never look at the Sun directly with a naked eye, camera or telescope. Why? Because you will seriously damage your eyesight and may become blind. Warning over. One of the ways of safely observing the Sun if you're an amateur astronomer is to fit a hydrogen alpha filter to your telescope. But if you were to do this as an amateur astronomer, the quality of the hydrogen alpha filter has to be checked first. Another way of observing the Sun is to use a telescope and place a black card with a small 1 to 2 inch diameter hole over the front of the telescope to reduce light. This protects the eyepiece as it reduces the amount of light going through. You then need to project the image of the Sun onto a screen, like a piece of paper. Remember, do not look through the telescope even with the card over the front, as it will damage your eyesight. This is why the image has to be projected onto a screen, so you never have to directly look at the Sun. 2. The Sun's diameter and distance from Earth. The Sun's diameter is 1.4 million kilometers. This is one of those numbers you just have to remember. Another number you have to remember isn't the astronomical unit. 1 astronomical unit is exactly the mean distance from the Earth to the Sun, and is used as a unit of distance between objects in our solar system. The reason why an astronomical unit is the mean distance from the Earth to the Sun is that the Earth's orbit around the Sun is slightly elliptical, so the distance from the Sun to the Earth is changing throughout the year. So the mean distance from the Sun to the Earth is 150 million kilometers, or exactly 1 astronomical unit. Remember, it is imperative that you say mean distance from the Earth to the Sun, or you will not get the mark. 3. The temperature of the photosphere of the Sun. To understand what the photosphere is, we must first split the Sun into layers. These are called the core, which is where much of the fusion takes place. Fusion is the process that provides the Sun with its energy. Remember, the Sun is not burning, it is instead fusing the cores of atoms together to build bigger and bigger elements. The next part is the radiation zone. Then we have the convection zone, and now we have the photosphere, where most of the light from we get from the Sun comes from. This is the visible surface of the Sun. Beyond this we have the chromosphere. It is nearly impossible to see the chromosphere as the light from the photosphere is too dominant. This image shows the photosphere and the chromosphere well. So now you know that the photosphere is the visible surface of the Sun. You will have to learn the scientific temperature scale. The Celsius scale, which is what most people use in everyday life to measure temperature, was designed so 100 degrees was the boiling point of water and 0 degrees was the melting point of water. The problem with this scale is that absolute zero, the lowest possible temperature, where the particles have no thermal energy whatsoever, is negative 273 degrees C. With Kelvin, the scientific temperature scale, absolute zero is 0 Kelvin. The difference between each increment, so 1 to 2 and 2 to 3, etc., is the same as in Celsius. So to calculate the temperature in Kelvin, all you need to do is just add 273 to the temperature in Celsius. All temperatures in astronomy and in most science are given in Kelvin. Notice that Kelvin does not have a degree sign, it is just Kelvin. So to calculate what 100 degrees C in Kelvin is, you just add 273 to the temperature in Celsius, which gives you 373 Kelvin. If you like, Kelvin is exactly the same as Celsius, but it's just pushed back 273 degrees, so it starts at absolute zero. Finally, the temperature of the Sun's photosphere is 5,800 Kelvin. 4. The Sun's atmosphere. This image by Soho shows the Sun's atmosphere well. There are two layers, the chromosphere, which we have already met, and the corona. The chromosphere is only around 2,000 kilometers thick. The orange disk is there to cover up the photosphere, as otherwise it would hide the corona as it would be so bright. The rays around the Sun coming out from it are called the corona. The corona is hotter than the chromosphere and the photosphere, even though it is further away from the Sun's source of energy. The corona is about 2 million Kelvin. If you're wondering what the funny line coming in from the left-hand side of the picture is, going towards the Sun, that is a comet approaching the Sun. 5. The nature of sunspots. Sunspots appear as small, darker patches of the Sun's photosphere. This is because the sunspots are cooler areas of the photosphere, therefore they release less light. This is due to strong localized magnetic fields. The concentration of the magnetic field inhibits convection to the surface, so less of the energy from the Sun's core and radiation zone reaches the area of the photosphere, therefore that area of the photosphere is cooler. When I say that sunspots are small dark patches of the photosphere, they're often about the size of Earth, so they're not really that small. You may notice that the sunspots appear to have two parts of them. The inner darker part is called the umbra, which is about 2,000 Kelvin cooler than the photosphere. And the outer part, which is not quite so dark, is the penumbra, which is about 200 Kelvin cooler than the photosphere. 6. The Sun's rotational period, or a Sunday? Unfortunately, this is not as easy as it sounds. As the Sun is a massive ball of gas and plasma, the third and fourth states of matter, the length of its day vary where you are on the surface. Due to the photosphere being a fluid, at the Sun's equator the length of the rotational period is 25 days. At the poles the rotational period is 36 days. So at the poles the rotational period is longer than at the equator. It's quite important to remember this because I'm sure it will be a multi-choice question and they'll both appear there, so you really have to be clear which one's the equator, which one's the poles. 7. Using sunspots to determine the Sun's rotational period. Remember, rotational period is the time to rotate, or a Sunday, if you like. As the Sun rotates, any object on the photosphere rotates with it at the same speed. As sunspots do not move across the surface of the photosphere, astronomers can use the angle turned through over a period of time to calculate the length of the Sun's rotational period. I'll give you an example. Say a sunspot here, after 5 days maybe here. The angle turned through is 60 degrees. 60 degrees is a sixth of the Sun, since 360 divided by 60 is 6. So if it takes 5 days for this sunspot to move across a sixth of the Sun, it would take 5 times 6, or 30 days, to complete a full rotation. Therefore, at that latitude on the Sun, the rotational period is 30 days. This is how astronomers determine the rotational period at different heights on the Sun, at different latitudes. 8. Movement of sunspots and length of solar cycles. A common way to view sunspots' positions on the photosphere is to plot their latitude, i.e. the distance from the Sun's equator in degrees. The diagram to show sunspots' latitudes against time is called a butterfly diagram, due to the shape of the pattern. To look at one, go to this link. On the butterfly diagram, it is possible to see that the sunspots come in a cycle. The length of that sunspot cycle, or the solar cycle, is 11 years. The diagram can be extended to see the number of sunspots included in each cycle too. the beginning of the sunspot cycle, At the beginning of the sunspot cycle, there are relatively few sunspots, and their latitudes are about 35 to 40 degrees. As the cycle continues, the sunspots tend towards the solar equator, with the latitudes of around 5 to 10 degrees, and the number increases too. At the end of the cycle, the number of sunspots greatly diminishes. Now for predicting the next year of the solar maximum. The solar maximum is the time when the solar activity is highest and the sunspots are most frequent. The question may give you some data and a chart which you will have to read off. The most important thing to remember is that the length of the solar cycle is 11 years, and that a solar maximum is not the beginning or end of the solar cycle, it is the peak of the solar cycle. I would really recommend practicing a few example questions. They are available in some of the past papers on the Pearson Edexcel website. 9. The Sun's source of energy, and all other stars as well, is fusion. As I told you in the last slide, the source of the Sun's energy is fusion. For astronomy GCSE, you need to know a bit more about what actually happens in the process of fusion. So, to show you what happens, let's start with some hydrogen. Remember, fusion occurs between nuclei, not atoms. So let's start with two simple hydrogen nuclei. These are the standard isotope of hydrogen. There is only one proton, otherwise it would not be hydrogen, as the number of protons defines the element, and there are no neutrons in hydrogen 1. So the core of the Sun is so hot that the elements inside it are in the fourth state of matter, plasma. At these high temperatures, the electrons are not associated with individual cores any longer. You just get a sea of electrons and nuclei. So when two hydrogen nuclei, remember these are just one proton each, collide, they form a proton and a neutron. At the same time as one of the protons turning into a neutron, a positron, which is an anti-electron, and a neutrino are released. So the two hydrogen cores have fused and turned into a deuterium core, which can also be called hydrogen 2, as it is a different isotope of hydrogen. Remember, the number of protons is still the same, so it's the same element. At the same time, the process has released some other subatomic particles and a lot of energy. Remember, deuterium is an isotope of hydrogen with one proton and one neutron. Then this deuterium core fuses with a hydrogen 1 core. This process does not release any subatomic particles, but a helium-3 core has formed. Helium-3 is an isotope of helium with 2 protons and 1 neutron. At this point, 2 helium-3 cores now fuse together. This releases 2 protons, and what we are left with is a helium-4 nucleus with 2 protons and 2 neutrons. This is the standard helium nucleus. In each stage of the fusion reaction, a tiny quantity of matter is lost and converted into energy. The amount of energy transferred by losing matter is defined by the equation E equals mc squared, where E is energy, m is the mass of the matter, and c is the speed of light. 10. How astronomers observe the Sun at different wavelengths of light. A hydrogen alpha filter only allows light in a very narrow range of wavelengths to pass through. What this means is that most of the light is blocked by the filter and only a select amount of light is allowed through. This increases the contrast of the image. A hydrogen alpha filter allows for safe viewing of the Sun and sunspots, active regions, filaments, and prominences. The hottest part of the Sun emit X-rays. So an X-ray image of the Sun shows the exceptionally hot corona, as well as active regions. This is because more X-rays are being emitted by these hot and active regions. To view in these parts of the electromagnetic spectrum only, either astronomers have to fit a filter like a hydrogen alpha filter, or they have to use a special telescope like an X-ray telescope. To have a look at what hydrogen alpha images and X-ray images look like, go to these links. 11. The solar wind. Solar wind is the name for the stream of charged particles that the Sun emits. Most of these particles get stopped by the Earth's magnetic field. Some of these charged particles get trapped in the Van Allen belts. Some of these charged particles get into the atmosphere of the North and South poles. These particles from the solar wind then cause particles in our atmosphere to become excited. And then upon de-exciting, these particles emit light. This light is called the aurorae.